a little bit?
No, I think let's go ahead and get started. Yeah, and just for
Yeah.
a bit of a housekeeping, we'll leave videos off except for the person who's presenting. And for the people who will be presenting shortly, please do turn on your video when you start to present. And for all the participants, please leave your microphone muted, as we'll run it in more of a webinar format. Any questions or things you want to share, please just use the chat to do that. Okay, I'll hand it over to you, Seda.
Thank you. Welcome all. It's very nice to have you all here at this webinar. I am the coordinator of this project. My name is Seda Çakırbenten. I think I had contact with most of you before. Well, I think you all know that we were originally planning this meeting to take place in Rotterdam. We organized a big event, a big stakeholder event there in March, but just that week, just before the event, 1 week before, I think, the whole pandemic outbreak began. So we had to cancel everything. And looking into other options, we thought we would like to hold this online event, a smaller version, and to catch up and to give an update about the project. And later in the fall, we are planning to have a bigger event, if possible, maybe in person, maybe online again. We will let you know more about this. So to keep in touch and to be updated, please sign for the newsletter. I think there will be more information about that at the end of the webinar. And we are now halfway in the E2C project, Electrons to High Value Chemical Products. It's been now approximately 2 years. And I think we can go to the agenda of today. So the reason why we are holding this webinar is to give you an update about the progress and also to get feedback from you. Just after this, Hutter, he is a principal scientist at TNO. He will give a presentation about the vision, background, and aspirations of this project. And then my colleagues from the consortium, they will give short updates about the direct and indirect conversion of CO2, the hydrogen production by electrolysis, dynamic modeling of PEM electrolyzers, and the valorization and implementation. And we will end the webinar with question and answers. So if you have any questions or any comments, please write them in the chat box during the presentation. So we will try to cover all of them afterwards at the end of this webinar. So I would like to give the floor to Earl if there are no questions or comments for now.
So with great pleasure, I'm standing here now, sitting here, to be quite honest. That's how we always start. But I'm really happy to be here and talk to you. A little bit pity that we are not sitting in the same room, Fred. So Seda, can you control the slides or?
I think Erin is doing it.
Erin, okay.
Yes.
Erin, would it be possible to go to the next slide? So, yeah, I'm old-fashioned chemical engineer. I've been trained with the same kind of pictures which you see over here in the 17th century. We are still working with just classical reactors. And if you go with one step further, Erin, to what we have now, the beautiful refineries, for instance, at Pernis as an example. This is basically the same thing that we have been doing already for more than 400 years, Fred. And now we are standing on a crossroad, Fred. Yeah, as a chemical engineer, I've been trained in building refineries. I know everything about how to build a refinery. That was basically what we studied when we were young. But unfortunately, since that period, we don't build refineries anymore. We close them down. So we have to think about what would be our chemical industry of the future. And the chemical industry is really important for this area of Europe. If you go one step further, Aaron, then you can see that in this small part of Europe, we are producing a serious amount of chemicals. 35% of the chemicals are produced in this small part of the world. So with Antwerp, the Ruhr area, and Rotterdam cluster, 35%. So that is really a significant amount of value which we're talking about. And now we have to do something completely different for it, because we need to go away from fossil. We have to have a reduction of CO2 emission by 2050 of almost 50 of basically 100%. So we have to do something completely different. So all these beautiful refineries, yeah, they will not be there over 30 years, not in the way as we know it now. So we have to build something completely new. And the thing what is completely new is, if Aaron, could you go one step further? That is basically trying to make a link between circular carbon and renewable energy. This is a picture which comes from the Nobel Institute, and it really explains it quite well. That in the far future, we have to get the whole cycle of carbon closed for it, and that basically means that we have to capture the CO2 and transform that into materials which we can use again. For it. Now, the CO2 can of course be captured via biomass, or we can get the circle closed via recycling, but we will always have CO2 which we have to do something with that. Now, of course, we all know that CO2 is basically almost at the end of the thermodynamic pit. We have to put energy in it. Without energy, you can't make anything. So the crux of this is really how to get the renewable energy sector coupled to basically the transformation of CO2. And basically there are two options which you can think about. One option is doing something with a molecule which has a higher energy level. So first making hydrogen, and with this hydrogen you can convert the CO2 in all kinds of products. Indirect, because you first have to make hydrogen. Then you have also the direct route, which you basically use directly electrons to transform a material like CO2 into chemicals, even up to ethylene, which is a seriously amount of value addition to it. And if you go to the next slide, yeah, you can say by yourself, yeah, this will take forever. But things can change quite fast. And it's a picture which I use often when I have to teach at the university. And I ask my students, do you see the car in this picture? And somewhere hidden, there is the car. But 13 years later, you have to spot the horse, because there is one horse there. And I don't know, yeah, thanks, that's over there. In 13 years' time, everything changed. And also, this kind of things we want to do can go fast if, and there's a lot of if we can have a significant breakthroughs in the amount of renewable energy production. Because the key of unlocking this vision is the abundance of cheap renewable electricity. Without that, it will be very difficult. But if you now see that we can produce in the Middle East renewable electricity at 2 cents the kilowatt hour, if you would have said it to me 10 years ago, I would have said, "Oh, that's never going to happen." But we are now in that neighborhood already. So can you imagine where we are going to be over 10 years further? Things can go very, very, very fast for it. And that's also when we look back at the initiation of this project. So if you go to the next slide, we saw that there will be renewable electricity production going on the way, especially in this area of Europe, between the Flemish region and the Dutch and the British coast. Significant amount of what we call variable energy supplies will be coming online in the next 20-30 years time. At the same moment in time, the industry with its massive assets, they are really under significant pressure to do something with that. And of course, the industries can capture the CO2 and put it on the ground. But yeah, that is not really a value addition. So the whole idea was now, why not try to think about what in Germany is often called the sector coupling. Try to couple these two sectors together and to show and to demonstrate that it's possible to get value out of the CO2 if I have enough renewable electricity for that. And that's basically what we saw. And we said, let's try to develop a project where we can demonstrate that this kind of things are feasible. For it, that people can really show, can be shown how it works for it. So if you go to the next slide, I think we started this whole endeavor in 2018 already. Time goes very quick for it, with 8 different partners in it, amongst others, well, the University of Sheffield, which should have been as well in this slide. But we started in 2018 and we went together on this pathway forward. And if you go one step further, Erin. Yeah, just one more. We set up the project E2C, electron to chemicals. Basically, in this 3.5 year, we are going to showcase 2 different routes, at least, to demonstrate that at a TRL5 level, to show that things are possible related to Power-to-X. And not only with these partners, which you see on the right-hand side, we also put a lot of effort in getting a community around it. And I see now more than 60 people in this webinar, so you're part of this community to really get more leverage on the things which we are developing in our laboratories for it. So if we go one step further, Erin. Yeah, what we said is, let's get maximum use of all the smart brains in this part of Europe, and focus on 2 different lines. One line focusing on producing dimethyl ether, which is a fuel. Of course, if you want to have dimethyl ether, you need to have hydrogen. So as well on hydrogen evolution. So that's basically the electrolyzers, which Seda just mentioned. And then we have the direct line, directly transforming CO2 into chemicals like formic acid. For it. And these are the 2 basically resource line. And because it is not only technology, you have to as well to think about basically what is the value. So what's the value chain? So you have to think about how does it fit in an overall story. So these feasibility studies are really important for that. And this is for us just a starter. So you would also like to reach out towards a broader community. So this educational, this summer school, this all dissemination is so important that we can really create that we can go much faster to this development period for it. So if you go now, yeah, thanks. If you go now to the different partners which we have here, TNO, we are working together with colleagues like Vito and the University of Antwerp on the direct line, but as well on the indirect line. This has to do with the history. When we started this, when we in 2018 started this journey, TNO, as we know it now, was not there. So we had an institute in the Netherlands called ECN, and TNO later merged together. Within the original TNO part, we looked at the predominantly direct line version. The colleagues from Patent, the ECN part, looked at the indirect line for it. So that's now that's point number 2. That's why you see ECN.TNO for it. Vito, as just mentioned, working on the direct line, especially on the electrode development. The group of Tom Breugemans from the University of Antwerp, working on the electrode material for it. And if you go one step further, Erin, then we have the University of Exeter working on the electrolyzer systems for it. the TU Delft working on optimizing the electrolyte, but as well working on the techno-economical evaluation and how does it fit in a total value chain for it. The University of Lille working on the catalyst needed for the indirect conversion, and as well, how are you going to operate this kind of system in a flexible modus? In the future, we don't have this steady state, but we will have much more flexibility in, or dynamics, better to say, related to electricity production. And the aid partner is the University of Sheffield, together with CO2 GEM, working on dissemination strategies and the roadmap activities for it. So you can see we had a lot of different, let's say, contributors to this, ranging from Germany, ranging from the Netherlands, Belgium, the Flemish region, for northern part of France, and UK for it. And what I really liked about it is that it was a nice combination, and is a nice combination of applied research institutes and academia for it. And we are supported by a broad range of companies. And you can see this beautiful list of all these logos of the observer partners. And I hope that we see each other later on at the end of the project when we are standing for the demonstrators, and you can, as the observer partners, and you can really see what has been realized for it, because now we are halfway. The exciting things are still to come for it. So if we go one slide further. So this was the start point. In a beautiful building in Antwerp in 2018, we came together and we set up with a very ambitious program. If you go one slide further, this ambitious program was really trying to go with all these different technology lines and try within this 3.5 years to really demonstrate the feasibility for it. And everybody who's working in technology knows how difficult it could be to accelerate basically from TRL3 to TRL5. There's a lot of things which need to be done. And the nice thing about it is because of the collaboration, it was way more easier to accelerate it. If people were just doing things within their own institute or their own university, this kind of project would not have been possible. You would not have made this kind of timelines for it. So if we go one step further, now why is it so important to work together? Now I give you a small example. This is a picture from my colleagues from TU Delft, from Tom Bardini for it. And basically what it says is if you want to go to really devices on the left hand of the picture, you really have to work, you have to have the knowledge on all the different things which is happening at the different scales. You have to know how the electrode material works on a nanometer scale. You have to know how the flow dynamics works in an electrolyzer. You have to think about how the stacks are going to be assembled, and you have to know how you can integrate it in a total system. And then you have to know on how it's going to be coupled to the industrial and electricity sector. So you can see there's a lot of things which you have to know at the different scales for it. And this E2C project is one of the few projects which I know which really tries to combine all these different elements in one project. For that's what, for me at least, makes it quite unique for it. So if you go one slide further. So let's take as an example the direct line. In the direct line, we are working towards formic acid synthesis. So at Vito, at the TU Delft, at TNO, we are working normally on grams per hour scale. Within the project, we have built, and it's just ready. So I could put a nice picture of it, the Electra system, which can operate at tenths of grams per hour. And mid next year, we are going to be at a demonstrator at kilograms per hour scale of formic acid production. So you can really see the scale up from a very small scale up to kilograms per hour scale. So that is really quite unique for that. And the same kind of thing is happening in the direct line, indirect line. So if you go one step further, in the indirect line, basically that's focused on dimethyl ether. Everything has now been done. The basic engineering is done. The PFD is done. The PNID is done. So we are ready to go and build the SEDMES unit, the absorption enhanced system to efficiently produce dimethyl ether. Now, all these details on the technology will come after my talk. So then my colleagues and the rest of the partners within the consortium will go much more deeper in the technology. But yeah, I will show you at least that going further, that we have the demonstrators we want to really deliver at the end of the project, that we are on time with that. Mid next year, both of these systems will be possible to be used for it. Then, of course, the question is, where are we going to do it? Now, I'm a little bit running before the music, running ahead for it. But the whole idea is to put it in the field lab in Rotterdam. For it. So the field lab is something which is like a let's say a test area for higher TRL activities. For it. And the whole idea is to bring these two devices, these two types of setups, and in the field lab to be demonstrated over there, to be really close to the industry. For it. So I really hope that at the end of the meeting, end of the project, we all meet over there and we can see the SEDMES setup and we can see the formic acid setup for it. So if you go one step further, and I'm almost getting to the end of it now, the field lab industrial electrification, that is what stands for FLY lab. There we have the possibility to work with these kind of setups under industrial relevant conditions. So we can mimic over there the dynamics for it. Dynamics are related to the electricity production. We can integrate it with CO2 capture, because you need to have CO2 as well. We can basically do something with the products which we have obtained. So this field lab is going to be one of the key elements to bring everything together. And if you go one step further, so basically in 2021, the pilot units should be ready so that we really can develop this and use it further on, going towards even higher TRL levels. For it. Now the field lab is now currently being coordinated by Voltegem, but as well E-Refinery. There's a TU Delft program on basically electrification is also part of that. Now I hope you have got a flavor of what we have been doing the last 1.5 year. So you have seen that we went from a very small scale to a much larger scales, and that we are now working towards demonstration for it and showing the real feasibility for it. What I didn't show you is that we worked also quite hard on basically understanding the value chain for it. And I'm also really happy that we have later on talk specifically addressing how does it fit in a value chain for it, and what kind of things are still needed for it. What I didn't as well went into much detail is about the electrolyzers. Now, especially for the indirect line, you need to have hydrogen available. So you need to think about what are now the best efficient hydrolyzers which you can get, which can be really integrated with this kind of system. So I'm also happy that later on you will get a presentation dealing with that. So this was the whole. This was the let's say the first 1.5 years of E2C, and I'm very much looking forward to the next 2 years where we really going to demonstrate the feasibility of our Power to X technology. And with this, I would like to conclude.
Thank you very much, for this nice overview of the project. As we will continue with the questions and answers later at the end of the webinar, I would like to continue with the updates in the different research lines of the project. We can continue with the direct conversion of CO2.
Yes, can you hear me?
Yes.
Okay.
Hi, Yuvraj.
Good afternoon, ladies and gentlemen. My name is Juraj Birja. I'm from Vito, one of the project partners in this E2C project. I will give you a short overview of the work we have been doing in this E2C project, and then on the direct electrochemical conversion of CO2. So you can go to the next slide, Erin. So the overarching goal in this direct line is to develop a showcase demonstrator for the electrochemical formic acid production. And as you can see in the scheme, we are working on the enabling technology and the demonstration of the technology. And you may know that you generally end up with formate when producing formic acid from CO2 electrochemically, as the process is usually carried out under neutral or alkaline environment. This means that downstream processing is required in order to obtain formic acid, which leads to extra costs. So to circumvent this additional downstream processing, we work on two parallel routes in this project and in the direct line of this project. One is where formate is being formed based on a typical two-compartment electrolyzer, and one in which formic acid is produced in a three-compartment system, leading to in situ separation of formic acid. Next slide, please. I will have some results and key achievements so far in the project. So first, the electrocatalyst development. One of our consortium partners, the University of Antwerp, they work on the development of the electrocatalyst. They look into two types of tin-based catalysts, tin containing n-doped carbon. You can see that on the figure on the right top. And this is based on previous work. They are also working on supported tin containing core shell structures, also on the top right, but then the second row. The partners have been able to reach current densities already larger than 100 milliamps per square centimeter and Faraday efficiencies of larger than 80%, which are the targets that that have been set for this project. In parallel, one of the other partners, Delft University of Technology, and then in particular the Kortlever group, they are studying the electrolyte. It is known that the electrolyte composition may have a large impact on the performance of CO2 reduction. You may think of the specific ionic species, pH, buffering capacity, etc. The partners are looking at these effects and try to optimize the system by introducing aprotic solvents and ionic liquids as well. Moreover, they study the compatibility of the membranes with different electrolytes and electrolyte mixtures, for instance, to prevent crossover of key intermediates or CO2 reduction products. Next slide, please. The partner Vito uses their expertise in the development of gas diffusion electrodes to study and to optimize the integration of the newly developed electrocatalyst in the gas diffusion layer. Together with the partners, we have been looking into the influence of the catalyst loading, the binder, the support material, etc. For instance, we found that using graphite as support instead of activated carbon, which is usually used with the same catalyst, of course, we reach higher Faraday efficiencies, but lower current densities. Another research topic that has been looked into is the reactor development. Partner TNO has been working on the design and the development of their three-compartment electrolyzer. And in this regard, the partners at the University Antwerp, they have studied the gas flow and modified the flow field from a convective to a diffusive gas flow. You can see that on the left bottom figure, where they show some different flow channels. It turned out that more CO2 was available at the surface, leading to a lower resistance and higher Faraday efficiency. Another important achievement was a strategy to avoid the salt deposition on the gas diffusion electrode via water injection. Now some words on the current challenges in the next slide, which are mainly on the electrocatalyst stability and upscaling. So our electrocatalyst is now stable for around 24 hours, give or take, which is far too low. The target in this project is set for a week. So currently we try to gain insight in the degradation mechanisms of the catalyst and the electrodes. Phyto and TNO, we have been working on the prototype bench scale system with the electrode surface area of approximately 300-400 square centimeter. You have seen the picture in the left bottom in Earl's presentation already, but that's the bench scale system built at TNO. So the key in this stage is to achieve the similar performance of our small scale setup, which is around 10 square centimeter. So currently we put everything together, bundle the insight obtained so far, and do a lot of troubleshooting and optimization. So in the next slide, our future work, we will improve the stability of our electrocatalyst and test our bench scale system and optimize the reaction conditions. And moreover, the pilot demonstrator, which is called Zeus, as mentioned before in Earl's presentation again, will be built based on an electrolysis stack containing several cells of the 300-400 square centimeter surface area. And we will use the experimental results of the bench scale system to guide this the building of this demonstrator. And I think I have, that was my overview. Yeah.
Thank you very much, Yuvraj. So as I mentioned before, there are some newcomers. If you have questions or comments, please write them in the chat box. We will cover these questions later at the end of the webinar. So now we can continue with the indirect line progress.
Okay, hello everyone. My name is Soraya Sluiter. I'm one of the project managers within the indirect line of the E2C project. And I'll be presenting this part. So if you can go to the next slide. So in the indirect line, we want to combine, like Earl already mentioned, an electrolyzer producing hydrogen from water, and then combining that with CO2 to produce dimethyl ether, or DME in short. And DME is a promising alternative fuel. As you can see, following these criteria on the picture, it's a very promising alternative if you compare it, for example, to other low carbon clean fuels. So within the project, as also been explained already, we have the enabling research in which several catalysts are being developed, both for the electrolyzer as well as for the DME synthesis. But we're also looking at the larger scale, at the demonstration systems where we will combine a PEM electrolyzer with the sorption enhanced DME synthesis unit, SEDMES. In the enabling research, we're focusing more on novel electrolyzer concepts, so the anion exchange membrane electrolyzers which will be explained later by the University of Exeter in more detail. In this presentation, I will focus on the DME part. We can go to the next slide. So we'll zoom in a little bit more on the DME production. So conventional DME synthesis is using syngas to produce DME, and this is a two-step process. So we have two catalysts. Actually, first methanol needs to be produced. If you go to the next part of the slide, first methanol will be produced, and then you have a dehydration step to produce DME. But both steps are thermodynamically limited. So if you look on the left graph, you can see you only have limited amount of DME that is formed, and a lot of byproducts, which leads to expensive separation steps in downstream processing of your DME process. So if we add a sorbent to this reaction, which then absorbs the water that's being formed in the reaction, we can enhance the selectivity towards DME. shifting the equilibrium, and by that we can increase significantly the yield of DME. And more importantly, we can actually use CO2 as a feedstock here. If you see the graph again on the left, first you can see that using CO2 you can very limited amount of DME formation, whereas if we use the SEDMES technology, we can go to over 80% of DME production and yield. One other thing that's important to keep in mind is that we need at least 2 reactor columns for continuous production of DME, as during the production the water is being adsorbed, but you also need a step where the water can be desorbed again. So we need at least 2 reactors to have a continuous process. So if you go to the next slide, that brings me to the results so far. We have designed this multi-column pilot demonstrator, which is targeted at 3 kilograms an hour of DME production. This pilot will be placed in a container so that it can be transported easily to other locations for testing, such as the field lab, as has been mentioned by Earl before. Also, the engineering and safety is almost done by now, and the procurement is ongoing. In the meantime, our partner, the University of Lille, has done some great work on catalyst development for the DME production reaction. They've synthesized, characterized, and tested several reactions, and we have a few good candidates based on palladium, copper, and copper zinc oxide materials. And these catalysts have proven to be stable for at least 20 hours in continuous operation so far. There are still some challenges with these catalysts. If you can go to the next slide, which is mainly the selectivity towards DME. This is still limited. They've observed some formation of undesired products at the University of Lille so far, but this might be different if we go to the sorption-enhanced reactions, because these reactions so far have just looked at the DME synthesis without a sorbent. So then another challenge is to optimize the DME productivity and selectivity. I already explained that you need at least 2 columns, but we've designed for 3 columns. Maybe it's easier to explain if we go to the next slide. Here I have an example of a cycle for SEDMES. So we have an adsorption stage in which the DME is produced, and then we need a regeneration, which is built up of several stages and which is usually longer than the adsorption. So we need to optimize the timings of the several steps that all reactors are undergoing to get a good trade-off between productivity of the system and also the DME selectivity. So this is ongoing work at the moment. Also, the next steps for the catalyst development is the testing of the newly developed catalysts using a sorbent. And here the target is to get, again, over 80% DME yield. And then last but not least, of course, we are very much looking forward to really building the pilot demonstrator and testing it within this project. So that's for my part of the indirect line. And now over to the next project partner.
Thank you very much, Soraya. Yes, we can continue with the next one. Hydrogen production update.
Hello, everybody. Is my voice is clear?
Yes.
Okay. So I'm Habib, a research fellow at University of Exeter. And here at University of Exeter, we are working on the development of catalyst along with electrolyzer for the production of hydrogen. So next slide, please. So as we know, we have a mature and commercially available proton exchange membrane-based electrolyzers in the market. But due to the use of platinum-based catalysts, this cell limits, this cell cannot be used for the industrial scale application. So here at University of Exeter, we are working how we can use non-noble metal and metal oxides as catalyst for the production of hydrogen. using electrolysis. So these non-noble metal and metal oxide can be easily used in alkaline media. That's why we develop an anion exchange membrane electrolyzers. The efficiency of this electrolyzer is basically based on the performance of catalyst, which is cathode, anode, and the resistance in the component of the cell. So if we minimize these things, so we can get high efficiency of the cell. In order to minimize the resistance of the cell, if we keep a minimum distance between the catalyst, cathode, anode, we can minimize the resistance, while the efficiency of the catalyst can be enhanced by designing catalyst with lower overpotential. So during electrolysis of water, oxygen evolution has sluggish kinetics due to the 4-electron transfer reaction mechanism. So this side's project need more attention. So we've had lots of attention for the oxygen evolution reaction side, how we can reduce the overpotential for the oxygen evolution during electrolysis. So next slide, please. For the development of catalysts here at University of Exeter, we use different techniques such as electrodeposition, spray pyrolysis, thermal decomposition, and beside this, we also use density function theory modeling, which has reduced our experimental efforts. Next slide, please. So a variety of catalysts we have tested and tried here at in our lab. And I have a detailed presentation on the catalyst development for the breakout session, where I will explain how we design and how we optimize catalysts with a lower overpotential for both OER and HER. So after selection of the catalyst with lower overpotential and high efficiency, we design a cell for this and electrolyzers, which is an anion exchange membrane electrolyzers. So we tested different parts of the cell. We optimized different parameters such as the concentration of electrolyte, different temperature, different membrane, different flow fields. And after optimization of these cells, we use our catalyst in this cell in order to test the stability of our catalyst and how this catalyst, for how long this catalyst can produce hydrogen. So we test the stability of our catalyst in this cell. And here from this graph, you can see that using our catalyst, we reduce the cell voltage by 200 millivolts at current density of 500 millivolt per centimeter square area. So far we have improved the efficiency of the cell by 5%. Next slide, please. So still we are working how we can reduce the overpotential of the oxygen sites, which is one of the challenging tasks, and still work is going on, and how our lab design cell, anion exchange membrane cell, can be used for the demonstration purpose. So we are also working on this, and we are also working on the accelerated stress testing protocols. So as this cell is novel and no one has reported these type of testing, so this is also under process. Next slide, please. So yeah, along with the how we can decrease the overpotential of the catalyst, especially the OER, we are also working on the HER side, like basically for the hydrogen evolution reaction, PGM based catalysts work very well. So, but they are very expensive. So we are working on this, how we can design non-PGM based hydrogen evolution reaction catalyst in order to reduce the cost. And we are also now testing our catalyst for more than 30 days here at University of Exeter. And finally, along with catalyst, along with the scale up of catalyst, we are also working on how to scale up the existing cell up to 100 centimeters square area, and to keep the voltage of the cell under 2. So these are the future work and still which is under process here at University of Exeter. So I think this for me now. Yeah, thanks for your attention.
Thank you very much, Abib. I think now we will give some information about the modeling part. Yes.
Yeah, hello everyone. My name is Sumit Sood. I am a doctoral student at University of Lille and part of the modeling group which is working in the framework of E2C project. So I will just briefly describe that what we have been doing and what we have achieved so far. So can you please go to the next slide? So this is a very basic slide representing that how the green hydrogen can be produced using the renewable energy sources through electrolysis. So this also lays the foundation for our work. We need to have some economical way to study the performance of the electrolyzer for producing hydrogen that is running on the intermittent sources, and to also study the effect of these intermittent sources on the hydrogen production as well as the health of the electrolyzer system. So keeping this in mind, so our first objective is to develop a simulation platform where we can do the simulation of the performance of different type of PEM electrolyzers running on the intermittent sources, and also where we can economically implement and test the algorithms for control and for the diagnosis and prognosis of such systems. So for this, there are certain challenges that we have to face. Can you go to the next slide, please? So the very first challenge is the intermittency of the sources of this kind, because we know that the energy is not available from solar or wind energy for the whole day or for the whole year. So we need a way to study these kind of sources, how they affect the system and how the hydrogen will be produced throughout the long term of the simulation. So for this, we also need to consider the safety concerns and the control algorithms that we are going to use for the electrolyzers, as the hydrogen is very dangerous to taken care of. And to do this, we propose to develop a model that we can use to study the effect of these intermittent sources on the electrolyzer. And that also is not a trivial task, because we have to deal with different multiphysics phenomena existing inside the electrolyzer, such as electrochemical, thermal, mechanical, fluidic, etc. And also, if you see these systems, this is also a combination of different type of components clubbed together which belong to different energy domains. And also here the dynamics of the system is also hybrid, and it contains both continuous and discrete dynamics that needs to be studied. So keeping this in mind, please go to the next slide, please. So the first objective is to develop a generic dynamic multiphysics model for the PEM electrolyzers that can be utilized for any type of PEM electrolyzer, irrespective of its configuration and the scale, which can be economically used for testing different operating conditions, different control algorithms, and the performance of the system. So we have developed this model for the PEM electrolyzer based on the bond graph approach, which can be used for the simulation as well as for developing different algorithms for diagnosis and prognosis. And also we have also incorporated the real-time efficiency for the electrolyzer so that we can study and we can simulate the performance of such systems. Can you go to the next slide, please? The second objective is to develop a supervision platform that can be used for the study of the prognosis and diagnosis for such systems, so that we can develop proper algorithms that can be used for the health management and for the smooth running of these kind of systems. For this, we use two different approaches combined together. So we use both model-based approaches and data-driven approaches for the diagnosis as well as for the prognosis of these kind of systems. So this is what we have been doing at the present. Can you go to the next slide? So once all this is done, we need to have a graphical user interface that can be used by a user to test different scenarios depending upon their system's configuration. So this is just the first version to show that how the system will look like, the graphical user interface, which can be used to test different control algorithms and diagnosis algorithms. This also gives us the flexibility of implementing different sensors in the system that can be used depending upon the configuration of the considered system. So we will be discussing this in details in the breakout session. So this is where I will conclude this presentation. Thank you.
Thank you very much, Abid. Yes, Rob will now continue with the valorization.
Okay, my name is Rob Stikkelman from the TU Delft. I'm only the presenter, so I would. This is the work of all the partners in this part of the project, so I would like to thank them. There we go. It looks if it works. Yes, it works. Okay, this is first I wanted to have a kind of time travel with you. We are going to 2040, and I show you the region, how it is in 2040 of the E2C regions. You see part of Britain, part of Netherlands, Belgium, and France. And over here, yeah, you see there are some chemical activities. Chemical clusters, and I define chemical clusters as a lot of chemical companies clustered together. This is an example of the port of Antwerp. And I see them all using CO2 and chemical and renewable power to produce their products. And as you can see, they have implemented all our nice PTX technologies. And basically they did that by, they had old systems out of the 2020s and they included all the new technologies. Okay, and so in 2040, we are really on the way to materializing our CO2 emission-free chemical industry. This is, of course, always a nice picture they tell you. But is it a realistic perspective or is it just a fairy tale? To explain this a little bit to you, I will go back to now and first go to the small details, and then I go to from a small scale, detailed scale, to a high level scale of clusters. Yeah. Here you can see the two routes we have been discussing in the previous sessions. It's forming formic acid or forming DME. And both routes have been studied in quite a detailed level of catalyst and so on. Now, I will continue on a higher level. I will look at the business case of these models. So what do we want to know? If we make a design of the two routes, then technologies are included, and some of them may be a showstopper. So what we'll use, we will want to know what kind of problems do we have in the design of these two routes. On the other hand, we want to know if these two routes are really economically attractive. So therefore, we need a business model. And the business model, it's the next one. This is the business model that is under development. And what we are doing here is we are looking at the inputs of the several routes. We're looking at the outputs. The inputs are, of course, electricity, CO2, and other feedstocks. And basically, there is some uncertainty about the prices. So we really do not know the amount of electricity, renewable electricity, and the price of renewable electricity. Yes, CO2 may be very cheap or even negatively priced, but we don't know, and so on. On the other hand, we want to calculate all kinds of aspects like the internal rate of return, net present value, and so on. Now, firstly, what we want to do is to use the results of this business case analysis model to guide our own research focus. So what are typical elements that are influencing the business case that we can change within the designs. So is it a problem of with good conversion, or do we have extremely expensive catalysts, and so on? So this gives us more insight to create a better business case. Yeah, at the moment we have already done some preliminary business cases, and we know a little bit about the strong and weak points of the designs, but we are not there yet. For the next steps, we really want to go into more validation of the business models, and there it always becomes a little bit problematic. As a researcher, you can use the information on literature and so on, but basically we also need some practical experience, and the practical experience is reflected in the parts, the people are just listening at this moment to this story. So we really would like to have some talks with you about the practical parts of the business case. Okay, this gives us information about the business case of the project. But yeah, I'm a little bit old, so I used to work a long time ago in refineries, but now I know that only a business case for a nice piece of equipment is really not enough. And therefore, a major part of the project we are doing is developing a roadmap. The roadmap is going from a demo, there it goes, to a commercial application of a PTX technology. Now, for that roadmap, of course, we need a nice piece of equipment, but we also need to study other steps. Here, I give you an overview of the steps we are looking at. We are not only looking at the two routes we presented to you, but we're also looking at other promising Power-to-X products. And of course, you have the scientific engineering, but very important are the financial and the regulatory barriers and opportunities. It's often can be a huge barrier or a huge opportunity. Now, we looked at what is the effect on regional industrial clusters, and we want to know a little bit about the locations of the inputs and the infrastructures. Now, here you see more steps that are commonly used in developing a roadmap, and we will develop them all. After we have a roadmap, we still have to look at. I give you here one example. This the inputs for the system. This is the CO2 sources, as you can see how they are now at 2020. However, we really do not know whether this is the case in 2040. It gives a lot of uncertainty. You see the huge peak at Tata Steel. Is it still there 2040? We don't know. This is for the CO2 sources, and basically you could think of that this is a kind of declining system. Another example is the offshore wind farms. This gives an indication of the renewable energy, electricity of offshore wind farms. Now, this is an increasing product, but we really don't know how fast it will go. And of course, it's an interaction between all other kinds of processes. Okay. Finally, if we have the roadmap and we have some ideas, we still have to fight with the puzzle how to change the current system into a new system. Of course, it will not be a greenfield project. We have to replace parts of the existing system and implement PTX elements. Now, this is a real tough job because we have to change something. Who will pay for it? Probably we need infrastructures. Who will pay for it? Hopefully, we will design a hydrogen infrastructure. And there are now two ideas to build a hydrogen plant in the Rotterdam port. It will result in a huge hydrogen infrastructure, but who will pay? And who will be the owner of the hydrogen? And where does it switch? And what are the contracts and so on? So this is a real problem, but it's also a good opportunity. Because in an existing chemical cluster, you it may serve as a fertile environment for a PTX option. For example, of course, production of hydrogen. Now, in the port, industrial port areas, there are enough consumers for hydrogen. So this could be a real, the demand is already there. Okay, for doing so, what we are doing in this project, we're building a kind of what we call a cluster model. It's a simple model based on mixed integer linear programming, and because we want to include a lot of surrounding activities surrounding the PTX option. And this way we are able to simulate the effects on this cluster as a whole. So what are our steps to do? We collect the data from the PTX technologies, sometimes based on the project, sometimes based on communication with other companies. We will describe a system with the surrounding systems, and we build up scenarios, and of course we'll run our models. They will all be focusing on the cash flow. And this will give a little bit insight in what is the effect of a PTX option in the complex industrial cluster. Now go to the final slide. Yeah, there it is. Now, is it a real perspective, what I showed you in the first slide? I don't know. I don't think it's a fairy tale, but I think when we are ready with our roadmap and our cluster studies, we can really help you to substantiate the approach to go to the system we want to have in 2040. Thank you.
Thank you very much, Rob. And with this, I would like to thank all my colleagues for their very clear and well-presented work for this great update to the project. And now we can continue with the question and answers. We have around 10 minutes, and my colleague Erin, she will moderate this session. And before that, I would like to mention that at 2:30, we will have the closed observer partner meeting. And if you would like to be an observer partner, if you are not yet an observer partner, but if you're interested, please get in touch with us. We would like to have you as an observer partner for this project. Then we share more information, more details about the project with the observer partners. Yes, Erin.
Yes, here we go. Good. So we'll open it up to open questions. Let me see if I can turn on my video as well. Yes, hi everyone. But I guess just to, as a little bit of a warm up and just to get kind of a feeling of who we have in the audience, we have a Slido poll set up. I hope everybody is familiar with using Slido. So I'm actually going to switch my screen here. There's this a Cozy 901. You can either join on your desktop or through your mobile phone. Yeah. Yeah. Good. So here's also the QR code that you can also join. We just have a few questions. I won't give too much time for them, but just get a little bit of things going for the rest of the Q&A. And then we have some questions from the chat that will also let the partners answer to as well. So if everybody can, as many people as possible can just sign on or join the Slido, and just this is just the first question to say, or to, get an idea of who we have involved in the meeting. Yeah, so please just type your answers. We'll just give a couple minutes. Yeah, 1 minute, maybe less. That's great. Okay. I have a couple more answers coming. Okay, perfect. I'm gonna go ahead and move on. Everybody can still join. You can join in the poll anytime. So let's go to the next one. This is just a multiple choice question. And again, if you're not able to join the Slido, don't worry about it. This will be just a quick thing, and then we'll get to the questions that have been specifically asked. And please feel free to continue to type in any questions in the chat of the Teams meeting. So other than formic acid and DME, which are being produced in E2C, what are the best products to produce using Power-to-X? If you think that it should be one of the options that's not listed, I see some people indicating other. It's good if you can type it into the chat of the Teams meeting, or I believe the Slido also will have a chat function. Great. No. Looks like methanol becomes a clear winner. Good. I'm going to go ahead and move on. Okay, so we have, of course, the drivers to develop Power-to-X fuels and chemicals, but from a sustainability standpoint, that's the key of this question. What's the most important factor for wanting to do Power-to-X? So again, focus on the sustainability. Okay. Great. Move on. All right, so this is the last Slido question before I go back to the presenters. So same question about what's the most important driver, but now from the commercial standpoint. Okay. Yeah, so it's much more even. Okay, great. A couple answers come in. Okay, no. That's very interesting to know. Great, so let me just go back to the presenters, and I'll ask the presenters to turn on their cameras if able. Let me just go ahead and actually we'll leave the cameras on. And I have a few questions, so I'm just going to go through what was typed in the chat box earlier. And there has been some discussion going on during the presentations as well, which is really great to see. But we'll see if there's any other points that should be brought up. So the first question I have was, what were the reasons for selecting DME as a product for the indirect line as compared to methanol? Anybody is welcome to join.
I don't know who has to respond to this. I think especially methanol is also a very good alternative to look at. And I am not sure if this is also being considered, for example, in the business case and the valorization line and compared to methanol. DME has a bit more higher energy density, so that's maybe one of the reasons. I wasn't involved in the project proposal, but I think methanol is also a very interesting alternative fuel to look into, but not in this project. I don't know, Earl, if you have an addition to that?
I think it was also, there were already some existing projects on methanol. So it made quite some sense to go one step further to deemed liter.
Yeah, and of course we already had some nice results within the Fletch project on the sorption enhanced DME synthesis, which we will also want to develop further.
Great. Any other comments on that? Good. And there was some discussion, but I just thought I would bring this one up anyways. It says, how can the two lines be compared if the products are different, DME and formic acid? It was one response that they're not going to be compared because they're developed in parallel. So I thought I would see if there's any other comments on that one.
No, this really, they are different things. So it's a little bit like apples and oranges. You should not compare them. Of course, you can look at per case, what is the techno-economical merits, which Rob and his team are well qualified for. So you can look per case, what is the techno and economical merits. And the merits, yes, that's something which you can compare. But of course, deemed liter as a product of formic acid, they have totally different applications. So I would not compare it like that.
Mm-hmm. Yeah, great. Any other comments from the presenters? And if anybody else from the project wants to join in, even if you didn't present, please feel free. So let me go to the next one. This was also already discussed a bit, but just for everybody. Why is there the stability decay? This is in for regarding the direct line catalyst. So why is the stability decay in 24 hours? And what is the process of material degradation?
Yes, I see that the person who asked the question just left the conversation, so that's unfortunate.
Oh, no.
But Tom Breugelmans already responded that it is actually not a decay in 24 hours. It is in the first few hours that it decays quite a lot to 65% or something like that, and then it stays more or less stable. And the reason for that is not clear. It is ascribed to a variety of causes, and amongst which also just the reactor design itself, the electrolyte, the integration in the gas diffusion electrode, because these stability tests were mainly for the electrocatalyst itself. So the 24-hour the decrease in Faraday efficiency in this case is for the electrocatalyst itself. But in the end, you need to consider the whole. So the electrode together with the electrolyte, the whole system. So yeah.
Okay, great. Good. See, okay, here's one regarding the electrolyzer work at Exeter. It says, as stability is the most serious issue for hydrogen production via the AEM, how do you want to prevent the catalyst degradation and increase the cell stability? Do we have somebody from Exeter that can give a response?
Yeah. Hello, everyone. I have replied to Marislav's question in the chat box, and Habib also replied. Yeah, I can quickly explain. That's very critical comments, and that is our research focus now. As I mentioned, we combine experimental work and computational modeling, DFT simulation, selected and optimized a number of catalysts. And so far, the stability, because in the lab, in the university, we test for a few days, and then we stop the experiment. And within our testing period, catalyst material looks quite stable. But of course, we will use SEM and other techniques to test the sample before and after operation. And in the meantime, now we focus on stability test and run under the continuous electrolysis and intermittent electrolysis mode, and to see the stability of the catalyst. And also we will focus on how to improve the adhesion of the catalyst material on the substrate. Another key component for degradation and cell stability is the membrane. And in this project, we at Exit, we don't involve develop new membrane. We just use the commercial available ion exchange membrane. We purchased more than 5 different types of membranes and compared in our lab. So the result showing is some results. And in the breakout session, Adeline will give you more detail, can show you the results with various members.
Okay, great. Thank you.
Question. Thank you.
Thank you. Good. We're a little bit over time, but I have one more question that I'd like to ask, and then we'll go ahead and wrap it up. So this is for the business case. Respect to the business case, how would you see the role of oil and gas hubs in implementing Power to X with existing infrastructure, little modification to export to the EU? It's quite the question.
Mm-hmm. Two visions. They could be it could be a positive effect, because at the long run they have the need themselves. So it's really the transportation hub and so on of whatever, of hydrogen. It's very important that you interact with the existing hub. On the other side, somehow it's of course a change of current business. So I think you always have to be. It could be a positive and a negative effect. Both of them are in. But I think when I look at the developments I see, for instance, in the port of Rotterdam, I really see that the attitude is in the right direction.
Okay, great. Thank you. Great. So we're going to go ahead and wrap it up there. I'm just going to throw up the links on the screen one more time. Yes. Yes, so please stay in touch with the project. Either join our newsletter, follow us on Twitter, or just keep a track of the website. So following this webinar, in 10 minutes, we are going to have an observer partner meeting, as Seda mentioned already. So that gives the chance for people who have signed up to join the project as an observer partner, gives them the chance to discuss in more detail with the project partners. It will be more focused on the hydrogen production and the indirect route, with also some discussion on the direct route and the valorization activities. But the most of the interest for today was in the indirect route. You still have time. If you want to join the observer partner meeting, please send me an email that you can just reply to the Outlook appointment request that you were all sent to have the link to join this meeting. So just reply there just to be directly, please. And then I can go ahead and send you the link for the observer partners, and we'll get you can join the meeting today and we'll get you signed up. Good. So then from my side, thank you very much to all the presenters and to everybody who attended. I don't know if Seda, do you want to say anything final?
No, I would also like to thank everyone for taking the time to join this webinar. It's great to host this, and I hope it was good for everyone to get some update of the project, and I hope we'll be more in touch. Thank you.
Great. Thank you, everyone.
Have a good day. Bye-bye.
Bye.
Bye.
That just
Bye-bye, Seda.
Bye-bye. See you later.
See you.